Chapter 5. LU Factorization. Matrix multiplication in the form of columns times rows. The learning objectives of this chapter are how to reduce a hard problem to two much easier problems, the concept of factoring a matrix into the product of two simpler matrices that are in turn useful for solving systems of linear equations. The outcomes are our first encounter with an explicit algorithm, LU decomposition, where L is a lower triangular matrix and U is an upper triangular matrix. We will use the LU decomposition to solve linear equations. And we will see LU factorization with row permutation. Previously, we learned to compute the matrix multiplication while multiplying rows times columns. Now we're going to do the opposite. We first partition A into its columns. Here A is 3 by 2 and we get two 3 by 1 columns. And we partition B into its rows. B is 2 by 2 and we get two 1 by 2 rows. The question is, what happens when we form the sum of the columns of A times the rows of B? First, we observe that columns of A are 3 by 1, while rows of B are 1 by 2. The product is defined, and it's a 3 by 2 matrix, the same size as A times B. If we multiply the first column of A by the first row of B, we get one 3 by 2 matrix. Similarly, if we multiply the second column of A by the second row of B, we get another 3 by 2 matrix. If we add them, we see that this is the same as A times B. Let's try this in Julia and verify our hand calculations. We define matrix A, we define matrix B, and we compute A times B, which is a 3 by 2 matrix. This time, we first multiply first column of A by first row of B and add that to second column of A times second row of B. And you see that we get the exact same result. In general, if A is an n by k matrix and B is a k by m matrix, we can write A times B as the sum of columns of A times rows of B. And we get k n by m matrix. And if we add them, we get A times B. Next time, we're going to look into LU factorization.